Previously, we looked at calculating probabilities with a binomial distribution, where each of the dots on this distribution tells us the corresponding probability of getting exactly that many successes. This was an example of a discrete distribution. Discrete because the values, the successes would either be 0, 1, 2, 3, and so on. Now we want to move into talking about continuous distributions. In particular here, we have what's referred to as a uniform distribution. It's called uniform because the probability of every single outcome occurring is exactly the same. And this is an example of a continuous distribution, because even though along the x-axis we still have the same values marked, there are also values in here of, say, 1.5, 2.25, 3.9, and so on. So all of the sort of in-between values, not just the whole number values, but those decimal values in between, are also possible outcomes. We can apply the uniform distribution in example 1, where we assume the amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 5 minutes, inclusive, as depicted by the graph below. We want to find the probability that a person must wait between 1 and 3 minutes. To do that, we would look at identifying the probability that a person waits 1 minute, and the probability that a person waits 3 minutes. And what we want to do is find the probability of those values and what's in between, meaning we're finding the probability that 1 is less than or equal to x is less than or equal to 3. As a quick side note here, with the binomial distribution and discrete distributions, it was important whether our inequalities were strict, meaning just less than or just greater than, or if they had that or equal to statement. But with continuous distributions, this probability is exactly the same as the probability that 1 is less than x is less than 3. And so essentially we don't need to worry about whether those inequality statements are strict or not. In order to find this probability, what we're going to do is calculate the area between the curve and the x-axis bounded between these two values. That is, we're going to find the area below the curve between x equals 1 and x equals 3. Since we're dealing with the uniform distribution, and that's just a straight horizontal line, we end up with a rectangular region, so we can calculate that area as just length times width. This rectangular region is 2 units wide and 0.4 units tall. So we can calculate this as 2 times 0.4 or 0.8, meaning there's an 80% chance that a person would wait between 1 and 3 minutes. In part B, now we want to calculate the probability that a person will wait more than 3 minutes for the bus. Let me write that a little bit differently. We're going to write this as 3 is less than or equal to x. That would be a correct statement because we'd be saying that they would wait at least 3 minutes, possibly more, but we were given an additional parameter in the original problem that the maximum here was 5 minutes. So even though it's not stated, we're going to go ahead and include this boundary so that x is bounded between 3 and 5. And now we're looking at calculating a different area, in this case between x equals 3 and x equals 5. We're still looking to calculate that area between the curve and the x-axis, or between that straight line and the x-axis, bounded between these two regions. We still end up with a rectangular region, so we would find the length times width, which again is 2 times 0.4, or 0.8, which is 80%. But the essential idea here is that when we're finding probabilities with a continuous distribution, rather than with the discrete distribution, where we looked at adding those individual probabilities together based off our probability statement, now we're looking at calculating the entire area bounded between the curve of the distribution and the x-axis, in between whatever our minimum and maximum values happen to be.